Greetings, fellow mathematicians. We're going to take a look at a difficult and tricky first-order linear differential equation. Now, this one is a little bit tricky because it's set up to fool you. You might be tempted to say p of x, the quantity multiplying y, is 3. However, this differential equation is not in linear form. You'll definitely want to check out the video linked down below in the description where we go through everything in detail to properly identify a differential equation in linear form. Here, we have something other than 1 in front of the derivative term. And that's why we're not identifying p of x as 3. Linear form, there's a 1 in front of that derivative. All right, our differential equation has a factor of x in front of the derivative. Let's divide it off. All right, and that should put it in linear form. We're going to get dy over dx plus 3 over x times y. And then don't forget to divide the right side by x. 1 power of x will cancel, leaving you with x times e to the x. And now we can properly identify p of x, which is 3 over x. And the rest of it is straightforward from here. So don't fall into that trap, missing the correct form for p of x here. I always give a question like this in my differential equations course. Your professor probably does too. That's not to trick you, but it's to make sure that you really analyze what linear form is. All right, now with that out of the way, we can go with the rest of the steps. We're going to calculate the integrating factor, but first we need to integrate p of x. All right, and that's really simple here. 1 over x, that antiderivative, is natural log of x. The factor of 3 is just a constant multiple, and that's it. So we now exponentiate that to get our integrating factor. The formula for mu is e raised to that integral or antiderivative. So what we get here is mu equals e raised to the 3 times natural log of x. And just be careful, this combination of exponentials and logs, while they are inverse functions of one another, they don't cancel. The basic cancellation rule is right here. You have to have e raised to just the natural log of something. The way we can get around that is using a property of logs. We're going to use it basically from the right side to the left. We're going to take a factor and then bring it up as an exponent. So let's rewrite this. Bringing up that power 3, we're going to get e to the natural log of x cubed. And now we can cancel the exponential and log. We get our integrating factor as x cubed here. Definitely be aware of that and try to simplify your integrating factors. This is a very common simplification that occurs with first-order linear differential equations. All right, now that we have our integrating factor, we're going to multiply the differential equation by x cubed. So we'll get x cubed times dy over dx. Here, multiplying by x cubed, 1 power of x cancels. We're left with 3x squared times y. And don't forget to multiply the right side by the integrating factor. That's going to give us x to the 4th times e to the x. The key step, which always happens, the left side collapses to the derivative of mu times y. So here, this becomes the derivative with respect to x of mu x cubed times y. All right, so let's go ahead and write down the differential equation. We have the derivative with respect to x of x cubed y equals the right-hand side, x to the fourth times e to the x. Now we cancel or undo the derivative by integrating both sides. All right, and this is where you want to be aware of some shortcuts for integration by parts. We're going to use a method called the Tabular Method. If you're not sure or already aware of that, check that out, link down below in the description. It is an incredibly awesome shortcut. Let's go ahead and implement that. We're going to calculate here the integral of x to the fourth e to the x. I'm going to set that up using the tabular method, setting it up as a table. Always start with a plus and make your same choices for u and dv. U is going to be x to the fourth, dv e to the x. U, you differentiate, so you'll get 4x cubed, 12x squared, 24x, 24, and then 0. The other side, successively integrate or calculate antiderivatives. And that's nice because it's e to the x all the way. All right, alternate your signs, plus, minus, plus, minus, plus, minus. And then we take our diagonal terms, multiplying by the signs, and those give us the uv terms. All right, and we can go ahead and write down our antiderivative and simplify it. Notice all the diagonal products contain factors of e to the x, so we can just factor that out and write our antiderivative here as positive x to the fourth minus 4x cubed plus 12x squared minus 24x and then plus 24. All right, and that was where we factored out e to the x. And of course, plus c. All right, and that is the antiderivative here. That is, again, a very awesome shortcut for repeated integration by parts. And if we write this down, we get x cubed times y. And there's our antiderivative. X to the fourth minus 4x cubed plus 12x squared minus 24x plus 24 times e to the x plus c. And that is our implicit solution. Now, if you want, you can go ahead and get an explicit solution dividing by x cubed, but that's really not going to give you anything nice. You'll get a lot of reciprocals, powers of x's in the denominator. All right, and that's it. Here, the problem really came down to a repeated integration by parts problem, provided you were aware that this was not in linear form. So always check for that. Check to see if your differential equation is in linear form. Check to see if there's something in front of the derivative term dy over dx. And here there was a factor of x, which is why we started by dividing by x to put it in linear form. Hope you enjoyed the video. Again, check out the tabular method, link down below in the description if you're not already aware of it. If you're enjoying the content, support the channel, like and subscribe.